Hey, welcome everyone to, I think it's the 12th or 13th coffee o'clock session. And yeah, this time we have Kunal Marwaha. Am I pronouncing it right?
You got it.
Yeah, okay. I'm not going to try it again. From University of Chicago. So Kunal, I actually got to know about Kunal's work mostly from Twitter, where he had posted about this initiative called Archive Wiki, where there are popular summaries of archive papers put up. And I'm like, wow, this is such a great idea. And I've not had a lot of chance to write summaries, although I've been one that's been something on my list for a while, but I've been reading them and it's actually very useful. So I'd recommend everybody to check it out. And also Kunal's website is also pretty cool. There was this really cool comic that I remember and I was like, wow, this is very interesting. And a lot of these things are very well aligned with thoughts that I've been having. And this is a cool person to reach out to. And yeah, and then reached out to him and we spoke a lot about QAA and all these other kind of things. And it was very interesting. The next obvious thing to do was to invite Kunal for a coffee o'clock session and to basically introduce Q India to Kunal and get things going, right? So Kunal is doing his PhD at University of Chicago, and he's been interested in a lot of in quantum algorithms and basically try and figure out where we can have an advantage. So he's been focusing a lot on optimization problems, and so today that's what he'll be mainly talking to us about. So yeah, with that, go ahead, Kunal, and then let's get started.
All right, hi everybody. Thanks for the introduction. Can you all see my screen?
Yes.
Okay.
Yes, we can.
Great.
Right, and also how does these question answer sessions go? Maybe just clarify that also, and then we get started. Would you mind people asking questions in between, or is it like towards the end? Or, yeah.
Yeah. So okay. So yeah, feel free to ask questions at any point during the talk. This is designed to be really geared at whatever you want to know. So I'm happy to talk at any level, like that's more public, like a more general audience, or more specific. I'll do the best of my ability as it gets more specific. But yeah, feel free to ask anything. And you can definitely contact me later and ask questions at the end. No problem at all.
Right. I think it's maybe good to keep it at a very public level and not go too specific, because
Sure.
I see a few people who are just starting out. So yeah, thanks. Awesome.
Cool. Okay. So yeah, I'm a PhD student in computer science at the University of Chicago. I work on a few different things quantum, but one area of my research is, are quantum computers good for optimization problems? And what I and some others try to do is study this question from a very theoretical lens. You know, I would say that there's several types of researchers out there. Some researchers are more of the, let's run things and let's try it. Let's do experiments or do computational work. And this work is mostly in mathematics and proofs. And what we're trying to do is we're trying to see if we can say anything good or bad about whether quantum computers are good for optimization. And we'll be using proofs and mathematics as our main technique. Okay. Let me see the chat. Okay, yeah. So this is kind of the general overview. I'll talk about why optimization. I'll also mention a little bit about two different words that come up in this work. One is called Hamiltonians and one is called cost functions. I'll talk about what we know and then the outlook, at least from my perspective. Okay, so why optimization? So most everything that you use or you've interacted with has gone under some kind of process of optimization, whether it's finding a shoe that was well designed for running or for walking, or using an application online that works for the thing that you want it to do. Most of these things involve some kind of optimization. And one way you could say optimization is you have a goal that you're trying to achieve using the minimum amount of cost or resources at hand. And so it's a very general way to say it, but there are applications everywhere in this, in optimizing things. Engineering, finance, logistics. And what's important to say about optimization is that the best solutions to any optimization problem are most often heuristics. And heuristics meaning like they're guesses. So in general, optimization is a very challenging problem. It's considered one of the more challenged, like one of the hardest computational problems in computer science in general. So we should only really expect to get, heuristics or best guesses. But what that means is that there always might be a new best method around the corner. And so unlike in some other settings where we know what the best thing to do is, and there's never going to be a better one, with optimization, there's always going to be, most likely always going to be better and better approaches to do optimization out there. And so because there's so many applications and because we don't know the best thing yet, many people in industries are looking for better ways to do optimization, whether it's bigger computers or different types of computers. We're always looking. And so I want to say a little bit about my work studies optimization from a very theoretical lens. And when I say theoretical, I mean like the papers I write have a lot of equations and proofs, and they're not as many simulations. And one reason that simulations can be kind of hard is because for quantum computers, we don't have very big machines. And so, however, there is a different time when people in computer science theory thought about optimization. They thought about this area called non-convex optimization. And they used to think it was kind of too hard. It was like really hard to study. And why would you want to have like this, machine learning with a lot of layers? That didn't really make any sense. But then what happened was the experimentalists and the computational people, they tried it and it worked really, really well with the big machines that we've been able to create in the past 10 years. And so, there's a little bit of a divide in the study of optimization between people who are theoretical, who kind of study it from a mathematics lens, and people who are, computational or experimental. And I think a lot of the people in the second camp don't trust the first camp because, the first camp was so negative about deep learning, and it ended up being a really, big success story, even if we don't really understand why it works. And so one thing that is important from my perspective, I think, is being able to tell stories about optimization that are, trustworthy. Yeah, I don't want to just poo-poo the whole thing because I don't understand it. I want to say, what do I know precisely and what maybe is still open. And so the picture on the right is actually, none of these are real people. So these are all generated images. And I wanted to give you a sense of like what people do with optimization. I don't actually know what application this is for, so it's almost a little scary. But all of these people on the right are made up. They they gave a machine a lot of pictures of people and they asked them to generate more people. So, the question is, are quantum computers good for this kind of stuff? And can we prove that they are or aren't is really the hard part. Okay, so I think really like it comes down to, can we use this new technology, this quantum computer for optimization? And I think that there's a lot of attention because if it might be useful at all, the people who do optimization for their job or for their industry, they're definitely willing to try. So they'll put a little team together or a company together, or they're going to put some money into new optimization strategies that might be better than what they already have. But we don't actually know if they're going to be, if they're going to be better. And more importantly, we don't know if we're going to be able to use the quantum computers of today. So right now people talk about noisy intermediate scale quantum machines. This called this NISQ era, the NISQ era. And what the NISQ era of quantum computing usually refers to quantum computers of today or of the next decade. And one question we want to know is maybe, if we're really lucky, we might even be able to use the quantum computers of today for optimization. And so I think we're kind of around the corner where we're starting to see the first times where quantum computers can do something that classical computers can't. And I think the main categories in my head are, sampling. You see these boson sampling or random circuit sampling experiments, simulation of, in the Feynman style, you simulate other molecules with molecules. But there's this new camp called really optimization for quantum computers that I think is getting a lot of attention as a possibility for quantum computing. Okay, so I want to talk about these words Hamiltonians versus cost functions. So some of you might have heard one or the other of these words. Hamiltonians comes from like physics, and in particular, some people in quantum computing use the word Hamiltonian. But if you come from computer science and optimization, you might be used to the word cost function. And so I'll try to connect the two a little bit. So a Hamiltonian is like the parameters of the quantum system that control how the system behaves. So usually in quantum mechanics, you have some Hamiltonian, which looks like a matrix. People use the big H for it. And they talk about, they have a differential equation where H is kind of the controlling operator. And so what usually people do is they try to find eigenstates or encode information in the different eigenstates of the Hamiltonian. So what that means is like at lower energy levels of the Hamiltonian, the system will behave one way, and at higher energy levels, the system will behave another way. And so the goal is to kind of use something about the energy levels to solve your problem. And so one really natural way to put optimization into, a Hamiltonian is use this cost function. And like I said before, optimization, at least the mathematical version, is you have some function that represents how good your solution is. And the goal of the optimization is to minimize that function. So the lower the function value, the better. So usually what people do is they say, well, whatever the function value is, that should be your energy level in the Hamiltonian. And so the most natural way to do that is every time you have like a constraint, constraints you can say are like penalties. If you don't make the constraint, you have a penalty in your cost function. Your number goes up and you want to get as low a number as possible. Well, every constraint could be a way to add to the Hamiltonian. So if you violate the constraint in the cost function, you also, gain energy in the Hamiltonian. So why does this work really nicely is because when you have really, really low energy in the Hamiltonian, you'll get more and more of these constraints that are satisfied, or a better solution to your optimization problem. And in particular, if you can get all the way to the bottom energy in the Hamiltonian, you're going to solve the problem exactly. And so that's pretty nice. Now we have a way to take our optimization problem, any kind of optimization problem, and turn it into a quantum computing problem where we design this Hamiltonian so that the bottom of the Hamiltonian is kind of the goal state of our optimization. Are there any questions so far?
Okay, great.
So someone asked, what's the algorithm to do this? So is this the algorithm for the fictitious people or for the thing that I was mentioning just now? Yeah, so in quantum computing, usually we design the Hamiltonian and we have to create this Hamiltonian. I would call this process, I don't know if I would call it an algorithm as much as a procedure to turn an optimization problem into the Hamiltonian. And so far, we haven't talked about what the algorithm is for quantum computing yet.
So there's no one algorithm to do it. Like if you have an optimization problem, you have to be creative enough to change it into an Hamiltonian. That's the question.
Yeah. So if you have a cost function, you have optimization problem defined by a cost function, then you want to use quantum computing. There are many, many choices you could do. I guess what I'm claiming here is the most natural thing you might want to do is make the Hamiltonian, like the energy values of the Hamiltonian, equal to the values of the cost function. But there are many other ways you could do it. And then once you have the Hamiltonian, you could minimize the Hamiltonian with a lot of different ways.
Okay.
Yeah, and I'll talk about some of the ways in this talk.
Okay, cool. Thank you.
Mm-hmm.
Thank you.
Great. So, okay, so the question, the optimization problem I want to talk about for this talk, and it's one I study a lot, is called maximum cut. And the way it works is you have this network, you input this network, and you want to split the network into two parts. Here, like I have a green region and a blue region. And what I want to do is I want to maximize the number of edges that go across the two regions. So these edges are listed in red in this picture. And one reason this problem, there's kind of two reasons this problem is really nice from a theoretical point of view. So one reason is because this problem is as hard as basically any other optimization problem. If you've heard this word NP hard, we use that language in computer science theory to talk about how challenging these problems are compared to others. So this problem is very, very challenging. And the second reason I think this problem is really nice is because the Hamiltonian, if you take the cost function, like I said before, to this optimization problem, and you turn it into a Hamiltonian, this Hamiltonian people already study in physics. People talked about Ising models and antiferromagnets. If people, when they were studying models of magnetism, basically studied this exact problem, but in a different language. So what I like about this problem is that there's a lot of research to pull from when studying this. And remember, because I'm studying it more from a theory point of view, it's nice to have other theorists to pull from. So, okay, so as was asked, like once you have this Hamiltonian, what do you do with it? And so I think there's kind of two very common ways people think about finding the ground state or finding the lowest energy level of a Hamiltonian. And so the first way that I think most people would start with is called annealing. And so what annealing does is, suppose you had a ground state of something you already knew. Like you could prepare a Hamiltonian where you knew you were in the lowest energy level. And then very, very, very slowly, you change the Hamiltonian you were in. You don't go too fast, but you go very, very slowly so that you eventually end up at the ground state of the second Hamiltonian. So what's happening is if you go slow enough, your system won't know that you changed the Hamiltonian on it. And so this process is called annealing. One thing you might want to do is make H1 something that you know and prepare the ground state of that and shift from H1 to the cost function that you were designing, this designed Hamiltonian. One challenge with this is that it's actually just very, very slow. So it will take a long time. It's not clear that they would be better than any classical computers. And definitely if you wanted to think about systems of today, computers of today, we probably couldn't do annealing, at least for problems that we care about. And so there's this other approach that was talked about called the QAOA. And I think this was really exciting in the beginning because what it does is it is like it's a little bit simpler, and it probably will work, but we don't have as many proofs about it. But importantly, you don't need a lot of time to find, maybe not the ground state, but something close to it. And the way it works is, instead of saying start in one and very, very, very move very slowly to the second one, you alternate between, like, the system is the first one, and then the system is the second one, and the system is the first one, and you kind of switch back and forth. And the hope is that if you switch back and forth in just the right way, you might actually stay kind of close to the ground state the whole time. And so, okay, so yeah, so the first way, just to explain again, the first way is you start in H1 and you go really slowly to H2. And the second way is you start in H1 and then you just switch to H2, and then you switch back to H1 and switch back to H2, switch back to H1. And you have to figure out what the timings are for that. But it might be a lot faster than quantum annealing.
Sorry, it might be a stupid question, but in either one of them, annealing or QAOA, once you reach to H2, how do you know what the ground state is now? What do you do to find the ground state for H2?
Yeah, okay, good question. So at the end, you'll have some your system will be in some state at the very end, and you don't necessarily know what the energy level of that state is without measuring it.
Right.
And when you measure it, you'll be able to get an energy value out. And people use these techniques. One common technique is called phase estimation, but it's a way to get the energy value out of the system.
Okay.
And so that's a technique you will get. It will kind of be random. Like you won't get the same, if it's not an eigenstate, you won't get the same energy level every single time, but you'll get an average depending on what the average energy level is.
Okay.
And so what will happen in a lot of these, a lot of this work is you won't be promised to get the ground state, but you might be able to get something kind of close. And so when I say kind of close, it means like you'll get a different solution to the optimization problem that is like almost as good.
Okay. Yeah.
Mm-hmm. Great. Okay. So for the rest of this talk, I want to talk mostly about this QAOA. And the thing is, the QAOA comes with a lot of promises. It says we can use optimization on a quantum computer. We can even use them in machines of this decade. And it might even be better than regular computers. And I think all of those things have to be true for us to want to invest in quantum computing for optimization, at least commercially, in the next decade. And so maybe some of you have heard this term VQE, variational quantum eigensolver. And I want to make a little bit of a difference between VQE and the QAOA. So VQE is often when you are trying to study a Hamiltonian that you haven't seen before. And so you have the system and you can prepare it, but you don't understand much about it. And so you want to do some optimization, but you're studying a fundamentally quantum thing. You're studying this Hamiltonian. And so I think I've considered the QAOA as like something like you're studying this classical thing. You're actually studying the cost function. And then you turn the cost function into a Hamiltonian to get the quantum computer to use it, to study it with a quantum computer. And so my personal take is that, like, I think the VQE setting is more general and also a little more natural because you're studying quantum with quantum. But the QAOA is like you're studying a classical thing, moving it to quantum, and then, trying to get an answer. And it's not, as you may know, there are classical problems like Shor's algorithm that solve, what we consider classical things, but on a quantum computer. So just because it's classical doesn't mean it won't work. But I do think the VQE is a lot more, natural. It's like using quantum for quantum. Okay. A question.
Hi. I'm Saurabh. I'm a master's student from NC State. I just wanted to say hi. And I had a question about your Hamiltonians, if you don't mind.
Sure, go for it.
When you translate your Hamiltonians to say a cost function, how do you know that you have like missed your state that you were trying to achieve? And how do you go back then? Because like in annealing, as you mentioned, you're using very small states to achieve your process. So how do you know what is small enough, and when do you overrun your state that you're trying to achieve? Like when do you maybe you crossed it accidentally, or you aren't able to achieve it because in convex functions you have a chance to like go beyond the point that you were trying to achieve. You miss your minima actually sometimes. So is that does that make sense, or is it like sort of different than what we are trying to?
Yeah, no, that what you said makes sense. So if I understand, you're saying in convex optimization, when you're trying to find the minimum, sometimes you overstep it. You go past it. And so you need to make sure that you don't overstep it and you go back.
Yeah.
And so in these problems, usually these problems are not convex. And so we actually don't know where the minimum is. And so in annealing, like you said, in annealing, if we go slow enough, if we make the time really long or the step size really small, we will stay in the bottom the whole time. But in this QAOA, we don't know. Like, and that's really the answer is, I would say QAOA is more a proposal. We still have to really test it out either theoretically or experimentally, because it may not work. There might be certain settings where it works and certain settings where it doesn't. But yeah, it's a very good question. Yeah.
Yeah. So in general, like it's an ongoing research, I guess. We are not really sure that we are going to reach the expected minima. Maybe we can reach something that's better than something that's been achieved, something like that.
Yeah, exactly. And I think one thing is, like in convex optimization, we can prove that we'll eventually get to the bottom.
Yeah.
Like we can write these mathematical statements that say, if we choose the right parameters, or with enough time, we always there's only one global minimum, or at least so in these problems, I guess I see the role of my work is to find some similar guarantees. I don't think we can guarantee something as good as convex optimization, but what can we guarantee? That's the ongoing research. Yeah.
Okay. Awesome. Thank you.
Mm-hmm. Okay. And I said theoretical guarantees, but like the theoretical guarantees are weak. I mean, and I think this is if you're going to take away one slide from what I study, I would say as of right now, and right now being, I don't know, August 20th, 2022, there are no proven optimization speedups on any near-term or practical problems. There is one case where we can prove that the QAOA does better than what looks like almost every algorithm. But then there's a paper I put out that 1 month later, there was a classical algorithm that achieved basically optimal. And it requires this, it does require conjecture, but most people believe the conjecture to be true. So, okay, so there's one little setting where I guess we haven't really nailed it down in one area. But really in many of the initial places people were looking, when the QAOA first came out, there was a follow-up work just a few months later that said, actually the QAOA is the best algorithm for some problems. And they showed which one. And it was really strange because it really was the best algorithm that people had written down. And it was so surprising because it was a quantum algorithm and it only needed one layer. It was a really low depth circuit. And so what people did is, a lot of computer science people came together and they said, well, that's really, really weird. And then they found a classical algorithm that does better than the QAOA. And this happened more than once. This happened twice. So I think there's a lot of hope that the QAOA might be, successful in improving over the classical algorithm somewhere. But I think what it's really teaching us is how much we actually know about optimization is just not that much. Because if this quantum algorithm that someone made up just a few years ago can beat it, like maybe we haven't thought hard enough about what strategies are good for optimization. So I think, yeah, so the real takeaway, at least for my work when I study theoretical guarantees, is I try to very rigorously say, how does the quantum computer perform with the QAOA, and how does a regular computer perform? And which one is going to do better, and in what settings? So I make up these kind of like test beds, these theory test beds, and show which one does better than the other. And so, yeah, so right now, there's one little case where I think it's maybe a little open, but we haven't proved anything so far. But I will say it's not like the door is closed. There are lots of problems we haven't studied, and we're looking for ways to kind of study them really generically, because we can't just list all the optimization problems and solve each one at a time. We'd like to be able to say, okay, for all these kinds of problems, the QAOA is either useful or it's not that useful. Yeah, there's a question.
Yeah, could you elaborate on the second time that the QAOA was proved classically?
Yeah, okay, so
it happened twice. Yeah,
it happened twice. So the first time it happened was right after the QAOA got posted. And I think that with that problem, it was even a better scaling. Like people talk about asymptotic scaling in computer science theory, and the scaling of the problem was better with the QAOA, which is really, really surprising. And I think, had that held up, it would have been a huge advance for optimization for quantum computers. The second time it happened was a little bit later. It was actually on the maximum cut problem itself. And it wasn't, this time it wasn't the scaling, but it was just the constant in front of the scaling. It was like, what's the performance of this? So there's some score that you get with the maximum cut problem, which is, let's say, the percentage of edges that you cut, or the fraction of edges that you cut. And it was going to be half on average, plus some little factor that depends on the degree. And the dependence on the degree is a square root. That's fine. But then there's a number that goes along with that scaling. And that number ended up being proven to be a little bit higher than what was known for the classical algorithms. So when people, I think out of the NASA Quail team, and there was an independent thesis that studied this QAOA again at level 1, they found that number was actually just a little bit bigger. But what happened was, if you did a calculation on the classical number, the classical number was bigger, but they just didn't prove it. They just proved that it was at least 0.30. And then the QAOA was like, look, we got 0.303. And then when you look at the number and you can prove the number, they just didn't decided not to prove it for some reason. The classical number is like 0.32 or 0.33. And so, okay, so these are really, really neck and neck. But one other interesting part about that algorithm is that algorithm is kind of like a QAOA that's not quantum. It works really similar as a QAOA, that classical algorithm. Where it kind of alternates.
Whose algorithm is this? Can you put a link to the paper?
Sure, yeah. I can.
After the talk.
I'll put a link at the end. Yeah, so the algorithm is by Hirvonen et al. It's a very simple threshold algorithm, and I can just explain how the algorithm works out loud. What happens is, suppose you want to take a network and you split it into 2 parts. So let's do this. Let's say everybody in the network just gets like randomly, I give it a color, either green or blue. Okay. Now, everybody should now look at their color and look at their neighbor's colors, okay? And so if you're green, you want to be surrounded by a lot of blue, blue color, because then your edges are going to get cut.
Yeah.
And so if you're green and you see too many green around you, you switch.
Mm-hmm.
And everybody does that at the same time. Everybody makes that decision once. So it's like a distributed process where like every node looks at its neighbors. If it's too similar to its neighbors, it flips. It switches sides. Okay, you do that one time. That beats the QAOA at level 1.
Hmm.
So that's the whole algorithm. It's not a very, tricky one, but it's, like it's kind of like a simple, like, there's a number of rounds and he only takes one round and it beats the
Right.
QA one round. And so I should say that the first paper I wrote was actually extending that to 2 rounds. What happens at 2 rounds? And it turns out
Right.
at 2 rounds, the QA does a little better. But at 2 rounds, this classical algorithm does even better. So one challenge with so that's the second time it looked like it was ahead, but I don't think it's really ahead. But I will say it's kind of neck and neck. Like there are algorithms that are really similar to the QA way that perform similarly, but we don't know if there's anything quantum going on.
Right.
And I should say
this. No, go on, please.
I should just say, like, of course, a natural question you should ask is, what about at 3 rounds or 4 rounds and 5 rounds? And I will say, it's been the real blocker it's been very hard to study the QAOA at high numbers of rounds up until about last year. So there's this paper I linked in the slides that we finally have a way to study the QAOA at many rounds. And we didn't have that before. So now we can do the comparison at, 3, 4, 5, all the way up, 10, 15.
So, yeah, and I think this is also a question in the chat. Like, could you elaborate what made it possible to go to higher rounds? And by rounds, everybody, it's just circuit depth. You add more gates to the register.
Yeah. Okay. So around in the language I was talking about is the QA way goes back and forth between the H1 and the H2. And the number of times you use H1 is the number of rounds. So 1 round, you go H1, H2. Second round, or maybe you do H2, H1. Then the 2 rounds, you do H2, H1, H2, H1. 3 rounds, you do, back and forth 3 times. So that's the number of rounds I'm talking about. And every round adds a few gates to your quantum circuit. And so, what happened in this paper that I was a part of is that we were able to find the right recursion. So in computer science, we talked a lot about recursions. And for many problems, this is not for every maximum cut problem, but for many natural maximum cut problems, a random graph, a random network has a really interesting structure where, like, the structure looks the same at every node. It kind of looks like a tree on both sides. Like, if you have a node, it's surrounded by a bunch of neighbors. And most of those neighbors don't talk to anybody else except their own neighbors. And most of those neighbors don't talk to anybody else except their own neighbors. And so you get this very tree-like behavior. And you can use that in your analysis to find a recursion. So not all maximum cut problems have this property, but many of them do, and a natural family of them does. And that's the setting where we're able to study the QA way at higher depth. Okay, some more questions.
Okay.
Yeah.
Yeah, so I have a question related to VQE and QAOS results. Okay, so I tried using VQE and QAOA for portfolio optimization. So in that case, I received that with respect to VQE, the lowest energy state was having the highest probability. And it was just one lowest energy state that had the highest probability. But with respect to QAOA, there are 3 to 4 lowest energy states, okay, differing by few points. But they all had the similar probability. So which results should I be more reliable? I mean, which results are more reliable with respect to portfolio optimization?
Yeah, so that depends on the problem that you have. But I think what it means, if 2 inputs have roughly the same cost function value, then they're just about as good as each other. They're equally good is what the answer is. And so what the QAOA and all these algorithms will do is they'll give you an answer with a good cost value. That's the idea. But it doesn't actually tell, there could be many solutions at that cost value or nearby. I think what you're finding is the QAOA is finding a bunch of different options that all have around the same cost value. But you get them with different they happen with like similar probabilities. And so the answer is whichever one is the best, the lowest cost function is the best. But I think, at that precision, I don't think you're going to see much difference. just by a small difference, the inputs to the optimization problem are probably similarly as good.
Right. I think let's continue with the talk, and then we can continue with the questions after.
Okay, sure.
Awesome.
Okay, so the other thing, and I don't want to talk about this too much. I'll just at a high level, and I can talk about it more after the talk, is one challenge that the QAOA has is it's what we would call, some people in computer science would call a local algorithm. And when I say local algorithm, it mostly just cares about interactions to its neighbors. And so, for example, on this maximum cut problem, the QAOA only cares about the graph structure nearby to every node. And one thing, kind of there's like a blessing and a curse associated with locality. The blessing is that it actually reduces the number of gates you need. So locality makes it a lot easier in general to run quantum circuits on today's devices because you don't need nearly as many gates. However, locality might actually be the very reason why the QAOA and many other algorithms are not very good. So there are some problems where we can even prove in a very mathematical way that any algorithm that is local for many optimization problems is not going to be the best one. And so, it's kind of frustrating because if you want to do quantum computing optimization, you want to find algorithms that have very low gate count. But what this tells you is you need to be able to do it in a way that's not just, local. And when I say local, I mean, I'll give you one little example, which is, suppose I was trying to solve the maximum cut problem, but I never could see the entire graph. I could only see my little section of the graph, and I had to make a decision. So I had to make a decision about, what color I should be, green or blue, but I can't see, the whole thing. So I don't know if I should be green or blue. It maybe looks like green, but what if I made the wrong choice? And those are the kinds of challenges that you run into from local algorithms. So I think the last thing is some people tell us there are some papers that show that QAOA has quantum advantage. And I want to clarify that the QAOA, when it has quantum advantage, it's about sampling problems. And it's similar to the other quantum advantage experiments that we've seen happen in the past few years, that when you sample from a distribution, the quantum computing has exponentially large probability distributions. And so those distributions are very hard to build classically. But just because it's hard to sample from a distribution, doesn't mean that distribution is very useful for optimization. And so I think to me, the intuition is that maybe because the Hamiltonian is already classical, that's what's making the problem not so good for quantum computers. But I think overall, what we're trying to see is we're trying to say, this is a little cartoon. It's not exact, but you have this black line, which is like the classical success. And you have these this blue line, which maybe one day in the future, quantum computers will be better than classical. But if you have these proposals like QAOA, which have a very low gate count or are local, they may or may not cross the black line. For example, this yellow line may or may not cross the black line. And so I see the role of my work is to be able to rigorously show, what cases where the yellow line might or might not cross. Because if the yellow line crosses the black line somewhere, that's where you would see the advantage. That's where you'd see a reason to use optimization for a quantum computer. Okay, so I'll wrap up now. What's the outlook? Should I use quantum optimization? And I would say from my perspective, right, a computer science theory perspective, we have very little justification that quantum computers today are useful for optimization. And in the future, we just don't really know. But I think really the answer is that people who do the quantum computing in practice may not care. because like I said before, the CS theorists, they could be wrong. Like we could maybe be missing some setting that if you just go and try it, you might find out. But I will say, I want to caution to many people that there's a lot of attention and what I would call hype in this area, because you have the word quantum computing, which is a new technology, and you have the word optimization or machine learning, which is also some very new technologies. And the second one has been very, very successful. And so if you put them together, I think there's a lot of hope, you know, that these new technologies, when you put them together, will have something very useful. But as of today, I would say we're not so sure that we have anything useful yet. It doesn't mean we should stop studying it. It doesn't mean we should like give up on it. But I think if we're going to find use cases for optimization on quantum computers, we're going to have to think a little bit harder about where that might be. So I think like the other applications like sampling and simulation and maybe even VQE might be more promising. But this is from my own perspective, from the computer science theory. And so I think like the money will keep coming because there are a lot of people who want it to work. But, you know, who knows? And so with that, thanks for your time. And you feel free to email me. My email is here and the slides are there and a link to my website too.